This is Project Hermes. Large language models are powerful, but they're slow. Every token requires a full forward pass through the model. So if you want a 48 token response, that's a 48 sequential inference steps, one after another, even on a GPU. Project Hermes changes that. Instead of one AI predicting one token at a time, we let multiple we let multiple draft agents propose several tokens ahead in parallel, then a central leader model verifies all of those proposals in a single batch CUDA forward pass, accepting correct prefixes and replacing only the divergences. On a GTX 1650, using a 4-bit quantized Qwen 2.50 leader model, baseline generation required 48 forward passes. Hermes reduced that to a single batch forward pass, achieving a 2.7 to 3.5 times throughput improvement, even with acceptance rates around 20 to 30%. And for Miro, this architecture scales naturally. Multiple users on different laptops can act as draft agents inside the browser, while a centralized leader ensures a coherence and quality assurance. Instead of one assistant, you get a distributed swarm, faster, scalable, and compute efficient collaboration. Miro now has the chance, through Project Hermes, change AI collaboration forever. Thank you. Hi friends, I'm going to demo Project Hermes, what it is, what it is not, how sampling is generated, the core idea of Hermes, how it is faster, and how it compares to baseline generation of tokens. All right, this block initializes the core components of Hermes, the tokenizer, and the leader model. We load Qwen 2.5 and configure it to run in 4-bit quantized mode using bits and bytes. Quantization reduces memory usage dramatically, allowing the model to fit inside a 4 gig GTX 1650 while still running on CUDA. The model is set to evaluation mode to disable training behavior and optimize inference performance. This leader model is the central verifier in the Hermes architecture. This function simulates a draft agent. Given a prompt, it generates multiple speculative tokens using sampling instead of greedy decoding, which you will see in normal LLMs. At each step, the model predicts logits for the next token, applies temperature scaling to control randomness, converts logits into probabilities, and samples a token from the distribution. This introduces diversity across agents, which is essential for speculative decoding. The function returns only the newly generated draft tokens and not the original prompt. Now this is the core of Hermes, the batch speculative verification engine. Instead of verifying each draft independently, the function verifies multiple draft agents in parallel using a single batch CUDA forward pass, CUDA forward pass per decoding step. For each token position, it constructs partial sequences, prompt plus accepted draft prefix. Oh, it's done already. Pads them to equal length and runs them together as one GPU batch. The leader model then predicts the next token for each agent. If the predicted token matches the draft token, it is accepted. Otherwise, the draft is rejected. At that position, and the fallback token is recorded. This continues until all drafts are either fully accepted or rejected. The key efficiency gains from batching verification across agents rather than running separate forward passes. That's the difference between uh, using agents, verifying multiple drafts, and uh, the usual baseline generation. This function measures traditional sequential generation performance. It generates tokens one at a time using greedy decoding, where each token requires a full forward pass through the model. CUDA synchronization is used to ensure accurate timing measurement. This baseline represents how LLMs operate in practice, strictly sequential token generation, and serves as a comparison point for Hermes. Now, let's compare them both. This function runs the full Hermes experiment. First, it simulates multiple drafts agents using sampling generate, which I have discussed. Then it is measured the then it measures the time required for batch verification using verify multiple drafts. It computes effective tokens as the sum of accepted prefixes plus fallback tokens. Next, it runs the baseline sequential generation for comparison. Tokens per second are calculated for both systems, and speedup is computed as the ratio between Hermes throughput and baseline throughput. All right, let's go to the results. Here, we're looking at the live performance results of Project Hermes. On the left, you can see the effective tokens produced by Hermes. As you can see, we have 12. These, these are the accepted speculative tokens plus fallback corrections. You know that those are from the agents, the multiple agents that we have generated. In the center, we compare throughput in tokens per second. Hermes is achieving significantly higher throughput compared to the baseline sequential generation. The key metric is speed up. Here we see around 2 to 3.5 times of improvement. But in this try, it was 7.68, which is significantly faster than the baseline speed. Below we break down each draft agent. You can see how many tokens were accepted before divergence and the fallback token that the leader substituted. This shows the speculative mechanism working in real time. Even with acceptance rates around 20 to 30%, because uh, we generated 48 tokens, right? Even with acceptance rates around 20 to 30%, batching verification across agents dramatically reduces the number of required forward passes. And that's the core idea of parallel proposals. Single batch verification and measurable throughput gains. And that's all. Thank you.